First up to share with you all today is Junyi Chu. Thank you, Junyi, for joining us. She joins us from Stanford, where she's doing postdoctoral research, but she's returning home because she earned her PhD here under Laura Schultz, who will be speaking in 2 talks from now. Junyi's research seeks to answer questions like, how do humans flexibly create, select, and solve new problems, and how cognitive processes change as we interact with others. So very relevant for games and agentic play. So with that, I will turn it over to Junyi.
All right. Thanks so much for having me here. The last time I stood on this podium, I was defending my dissertation. So I'm going to try to have a little bit more fun today than a couple of years ago. All right. So I study play in children and adults and all kinds of other humans in between. And I'm interested in questions about learning and motivation. I've titled today's talk Playful Problem Solving because that's what we're here to do. We're going to play games, and in the process, we're going to solve the problem of general intelligence, right? That's our path forward. So to prepare for this afternoon, I played through all the ARC 3 preview levels to see what I would have to say about using games to measure intelligence. If you haven't played it, I'm sorry for possible spoilers, but I had so much fun. These were such great games. I really liked it. But it wasn't so much the individual levels or individual games that were fun, but it was really satisfying to complete all of them and see how fast I could figure them out. But it was really the process of learning and guessing what the objects were and what the rules and interactions were that was interesting to me, right? And I think that's what maybe Lanzing would call role model induction, right? That kind of learning process was really interesting. But I had also a lot of other thoughts that bubble up as I was playing this benchmark. Like, wow, how did you come up with this game? Like Hunter's Team, that's so cool. How did you figure that out, right? How did you invent that? Or in that very bottom left game, I was like, I see how you're trying to trick me with all the distracting colors, and I'm not going to be distracted by that. Or I really like the orange game in the bottom. I was thinking, I really love this idea of flowing water. Are there going to be lasers too? Like, what else is coming next, right? These kinds of thoughts, are they helpful for solving the immediate task of passing the level and, winning this benchmark? Probably not. I was probably on the right-hand side of the curve that was shown earlier, right? But would we and should we expect a generally intelligent agent to at least be able to entertain these kinds of thoughts? I think yes. Because I think the distinctive thing about human intelligence is not simply how well we can solve even novel problems that are presented to us, but it's all these other thoughts and new problems that we can come up with on our own. I think curiosity is certainly important, right? Intelligent agents should be able to reason about other people's goals and mental states. We should be able to distinguish between what's important versus distracting and appropriately control and allocate our attention, right? And of course, we should be able to reason flexibly about different abstract concepts, including ones that we haven't seen before, or maybe don't even exist in the world yet. Okay, so how should we measure this kind of flexible intelligence, right? The way I've been thinking about this in the past 2 days, since I knew about this event, is that we should begin by considering what people are really learning when we learn to play a game. What is the learning, right? What kinds of skills and tasks are we figuring out how to solve? So in my postdoc, I've started examining these kinds of questions using this particular game. Some of you might know it. It's called Sokoban. It was invented in the 80s. It's a classic kind of puzzle game, right? Very much like the ARC 3 kinds of tasks. So if you know this game, can you give me a thumbs up? Okay, some people know and have played this game. Thumbs down. Okay. If you don't know this game, but if you just look at this picture and feel that you can confidently infer the rules and goals of this game, give me 2 thumbs up. Wow, okay, really rapid learning. Okay, awesome. So it's kind of subtle. In this particular UI from sokobanonline.com, which is a wonderful website, there's a tiny red dot in the top left corner, right? And you're supposed to push the brown box over the red dot, and you can only push, you can't really pull. So you can kind of get stuck in corners if you do the wrong thing. And this is a really difficult benchmark, it turns out, for AI and planning because it's sort of really long horizon, long depth. You have to think like many, many steps forward in time. But when we learn to play a game, we learn many other things. So I'm just going to give you a couple examples. One, we can quickly learn what levels are valid and even belong in a puzzle set. So for example, that would be a terrible level to play, right? You could have an RL agent move around a ton and they wouldn't figure out, right? So intelligent agent, I think, is not one who keeps bumping up against a wall and can't give up and switch to more interesting tasks, right? I think intelligence should be used to decide what problems are even worth pursuing in the first place. Here's another one that's actually also pretty bad. It looks more similar to the example, but it's also a bad level. It's not solvable. And here's a puzzle with 2 boxes, so more visually dissimilar than the example, but is actually solvable. We can also make inferences about how difficult a level looks. So on the left, you have a puzzle with 4 boxes. You have 4 sub-goals, actually. But it's a lot easier than the one on the right-hand side that only has 2 sub-goals to figure out. So difficulty judgments aren't always straightforwardly tied to these visual or physical features. We can also ask about more sophisticated questions, like what kind of strategies or moves are required on this particular level. So if you look at this, you can try to imagine and run your mental game player engine forward and try to solve this puzzle. And maybe you can see the kinds of moves that are required. Let me see if the video works. So that's just me playing this game and slowly walking through it, right? And you can kind of start seeing forward. I'm just going to keep pushing it around, and then maybe I'll have to do a U-turn at the very end. And then you can look at a new level and ask, does that require the same strategy? But you can also make new levels. So can you make one that's going anti-clockwise instead? Can you make a puzzle with the same idea but S-shaped instead of going in a spiral? For 2 players even? So you can really start inventing new games and with the benefit of certain abstract concepts that maybe we've borrowed from other games or just come up with on our own. And I think most importantly, what's fun, right? Are you going to enjoy this level or is it tedious? It's kind of visually really interesting, right? But is it fun? And of course, if we have all these things, we can also use them to reason about social things. So like if I played you 2 videos of people solving the game, you can infer who is more skilled, maybe even who's having more fun, right? Okay, I'm gonna skip ahead because I want to tell you at least like one data point before my time is up. So in my postdoc, we're running this study on human puzzle solving, and we're doing Sokoban, slightly different user interface, it's blue instead of yellow. And we've collected quite a bit of data. So we've got human participants, most of them naive to this game. We give them like 2 or 3 tutorial levels, and they played up to 8 puzzles for up to 5 minutes each. So we have 2,000 game records. And we're most interested in how people judge how enjoyable or difficult a puzzle might be. And unlike the ARC3 tasks, actually, people overwhelmingly thought that our study was hard. That's a blue histogram on the bottom. These are really hard levels to figure out, actually. They only have 3 boxes. But we've got quite a good spread in enjoyment ratings. So the question we've been pondering is why? What makes people think a puzzle is fun to solve? Well, the first answer is whether they succeed. So if they finish a level, they say that was a lot of fun. If not, they're not having that much fun. Okay, maybe not that surprising. But I really wanted to test some of the things that even Francois mentioned about like learning progress and things of that sort. So we thought we'd get a bit more signal and data. So we looked at the number of steps they took. Is it efficiency? So if you look at the blue graph, we see that people who solve the level in fewer steps report having more fun. Okay, so efficiency is enjoyable, probably. But there's still a lot of noise. If you look at the people who never solved the levels, sometimes they're having fun, sometimes they're not having fun. And we don't really know why. Like what kinds of struggle is more interesting, right? And feels like learning versus not. So we don't really have an answer, but I'm going to show you some visualizations we've made of the data. Here's a player who's pushing the diamonds around, and you win by putting everything on the yellow boxes, on the yellow tiles, and that's great. They get a bit of confetti animation to reward them. And the way that we're visualizing it is in 2 ways. So on the middle plot, you basically see a progress by line plot. So there's this red area where you can get stuck, and if you get into that kind of game state, that means you're never going to solve it. And so they initially get a little bit stuck, but then they very quickly rise and make progress to figure out the level. On the left-hand side is a state space visualization. So these are all possible arrangements of the agent and the boxes and everything. And we can kind of visualize how they're exploring that space. Now, other people don't figure this level out as quickly, and you can kind of see them just getting stuck in that red zone. And I'll just sort of play this animation so you can see. Oops, that's not tied together. Okay, it's going really fast, but the main takeaway is that this player is really stuck. And how can we start to analyze the kind of learning that's happening in that exploration, such that by the end of it, somehow in 5 minutes, they suddenly figure it out, right? How are we supposed to analyze this kind of strategic learning? That's, I think, a real open question, and I'd love to talk to people who thought about that. And I just want to end by saying that, when we study human play, right, the idea here that I want to talk about is that we're not just solving problems, we're assessing problems, we're choosing problems, we're making new problems of our own as well. And if we really want to start understanding more general forms of intelligence, I think these are 2 kinds of questions that we could start asking, right? What is being learned, right? When an AI is good at solving a level, what else should it be good at? What kind of generalization are we thinking about? Okay, thank you so much.